So we understand a function as doing something to a variable, which raises the question, what if we want to do more than one thing to a variable? For example, suppose we have these two very simple functions, right? I've presented these as relations, as collections of ordered pairs, but we can also think of them as collections of inputs and outputs. So f takes the input 1 to the output 3. That's what the ordered pair 1, 3 is telling me. It takes 2 to 5. That's what 2, 5 tells me. It takes 3 to 7. That's what 3, 7 tells me. It takes 4 to 9. That's what 4, 9 tells me. Similarly, we can think of G the same way. It takes the input 9 to the output 3, the input 7 to the output 1, the input 5 to the output -1, and the input 3 to the output -3. And you'll notice that the range of f, the possible outputs of f, are the same as the domain of G, the possible inputs of G. So we might ask, what happens if we do f and then do G? What happens if we say, take the number 1, and we do f to it, which gives us 3, and then we do G to 3, right? So G of 3 is -3. We end up with this new thing that takes the input 1 and gives us the output -3. Similarly, if we start with 2, f takes that to 5, which G then takes to -1. Our new thing takes 2 to -1. F takes 3 to 7, and G then takes 7 to 1. Our new thing takes 3 to 1. F takes 4 to 9, and then G takes 9 to 3. Our new thing takes 4 to 3. As you can see, putting those two together gives us a new function, and this new function has a name. This new function is called G composed with f, which we write as G small circle f. Now that order might seem weird, but we'll see the reason for that order in a little bit. So this new function, we should label it G composed with f. Sometimes we'll just write it as kind of a leap over combining the two. Just as we could see our original functions as sets of ordered pairs, we can, if we like, also see this new function as a set of ordered pairs. While we can think of the composite function as also a set of ordered pairs, it's much easier to see the connection when we think of the function as one of these input-output tables. Okay, so we did f, and then we did g. Why did we write them in this order? Why did we write f second, even though we did it first? And the answer to that has to do with the function notation. It's because if we take the function g composed with f and apply it to a number, if we apply it to some specific input, in function notation, well, that means we take f of x and we do g to it. When we write it in function notation, the letter f happens to come second. even though it's what we want to do first. And so for that reason, we also write the letter F second in composition notation. What do I mean by that? Say we wanted to take our G composed with F and apply it to 3. According to the actual listing for G composed with F that we found, G composed with F of 3, that's just 1. But notice that F of 3 is 7. So G of F of 3, that's going to be G of 7, which is 1. I'm going to give you one of these to try, just to get some practice with this idea of composition. So I'm going to give you a pair of functions listed out, ask you to compose them, and ask you a couple of questions about them. So suppose F is the function that takes 5 to negative 2, 7 to negative 5, 9 to negative 8. K is the function that takes negative 2 to 2, negative 5 to 3, and negative 8 to 4. First find K composed with F of 7, practicing with the notation. Then make an input-output table for K composed with F, just like we did earlier in this video. And finally, list K composed with F as a set of ordered pairs. Pause the video and try this now. Okay, so K composed with F of 7, that's going to be K of F of 7. F of 7, we see 7, negative 5. So F of 7 is negative 5. Thus we're taking K of negative 5. Well, we see negative 5, 3. So K of negative 5 is just 3. Thus, K composed with F of 7 is just 3. To make the complete input-output table, K composed with F, that means first we'll do F and then we'll do K. So F takes 5 to negative 2, it takes 7 to negative 5, it takes 9 to negative 8. K takes negative 2 to 2, negative 5 to 3, negative 8 to 4. So our input-output table for K composed with F is 5 goes to 2, 7 goes to 3, and 9 goes to 4. As a collection of ordered pairs, K composed with F is just 5 goes to 2, 7 goes to 3, and 9 goes to 4. So that's all there really is to composition of functions. In the next video, we'll see how this works with functions that we actually have algebraic expressions for.